Hello, my name is Justin Hickman. I'm with Vertispan. Today is May 11th, 2023, and this week I'm changing up a little bit, not too much. I'm probably going to be switching projects in the next week or so, but for now I'm still going with the GWT database kind of stuff. But let me go ahead and switch over to my display real quick, and we can just go over some stuff. So as just taking a look at CouchDB, which is one of the things that I was modeling after, or PouchDB, which is a JavaScript version, and I found this blog article basically confirmed what I was thinking in regards to the B tree. So it talks about using a B tree throughout, but if this, if we take a look, that's a little bit too close. Basically, it's using a B plus tree, which is the variation of the B tree. And that makes a lot of sense for the indexes, because if we take a look at the B plus tree in comparison, all of the keys, rather than just being distributed throughout all of the different nodes like they were before, all of the keys, there might be duplicates, but the values are always going to be in the leaf nodes. So you see right here, you have a 3 that also is in this leaf node down here. And then we also have all of the leaf nodes connected through a linked list approach. That way you can find one and then be able to iterate over all of the keys much cleaner than having to traverse the tree just to find the next node. And that makes a lot of sense for some of these database queries that we're going to do with the indexes. Being able to look at all of the numbers greater than 3, for example, you would find the 3, and then you would just start traversing across this without having to do those additional lookups. So I think that would be a good change for the GWT database side. So I started working on some of this. So basically, you just have all of these different characteristics. This is on Wikipedia, but it just shows that you can have a maximum record stored, maximum keys on any particular level, and all of that. So then whenever you add or remove, there are certain rules that you have to follow. And I started implementing that internally, but then I decided to create a unit test because it was a little difficult to actually test these B trees in an easy way. So let's just go through the code that I've developed so far. I actually got quite a bit of it done in this last week. I still need to do the traversals, and removes are kind of weird. And I also need to figure out what to do in regards to duplicate entries, because obviously a B tree is intended for unique keys. But if any of those keys are duplicated, which they would be, let's say that you're indexing your database on last name. Well, obviously there's going to be multiple people with the same last name. So how do we deal with those sort of situations? Those are things that we're going to figure out as soon as we actually get a B tree implementation that functions. So let's start out with the normal B tree class here. Just as I was before, even though this is a B plus tree, I just called it B tree for simplicity. I put it in a different package so that we don't have to worry about interfering with all of the B tree work that we did before. This will probably eventually go away and replace all of what we've done so far with the B plus tree. So in here, you construct it with the number of degrees, which is basically the maximum keys that you can have on any particular level. And it's probably best to show this in a visualization. So this is the University of San Francisco website. They have this really nice gallery of different algorithm visualizations. This one's pretty nice. So if we set like a degree of 4 and we just start adding, it'll animate this. So the very first one, we see a 1. That is a little hard to see on this canvas. 500. Oh, it's not zooming in. How do I zoom in? I just increase the size of the other browser zoom. There we go. So let's insert 2, and we can see that it inserts in here 3 and goes up to there. But because the maximum degree is 4, the very first or the very next one that we add is going to basically split this leaf node into 2 groups. So let's insert that again, and you can see that it broke off with the middle number as the root node, and then we have 1 and 2 over here, and 3 and 4 over there. And of course, you have the connection between the 2 and the 3, so that you would be able to iterate all across this. So just keeping adding on, we can see that it'll add one here, and then the very next one that I add, it'll actually break that one up and move that root up into this internal node. And because the internal node's not full yet, it would still be able to add at least one more before it has to break up into multiple nodes itself. So let's keep going. So we have the 7 there, and this one will break this up and then move one of these. Yeah, thank you. One of these up into the other root node. And let's keep going until we fill this guy completely up. There we go. And that broke up into 2 different groups. And as you can see, we have 7 here. And the basic way to traverse a B+ tree is you look at the node and the keys that are on it. You know that this is not a leaf node because it has children, but anything less than this key is going to go down this side. Anything greater than this key is going to go on the right hand side. So anything less, if we're looking for 6, for example, we know 6 is less than here, so we come down here. It's not less than 3, it's not greater than 3, and less than 5. It is greater than 5, so then we come down here, and then we end up finding the leaf node that contains the 6, and most likely this will contain a value associated with that key. And of course, with the delete, we have the same sort of mechanism. We delete this, it finds it, removes it, and because we still have one item in this record, we don't have to do anything. But we're going to get to that at some point. So I broke this up into a node, which is the parent type for both the internal and the leaf nodes. So looking at the Wikipedia page, you can see that where is that? Internal nodes and leaves. So that's basically what the tree is consisting of. So if we look here, we have the other node, we have an internal node, and we have a leaf node. And each one of those do slightly different things whenever you're adding and removing and searching for the items. So if we just look at the other node, we're taking a comparator and the maximum number of keys. Here I use max keys instead of degrees. That way I don't have to do a -1 every single time. because all of these are internal and typically won't be exported or visible outside of the B tree, because the B tree is going to be the front controller for all of this, and all of the actions such as add, remove, search range, anything that we have as a global operation will be fronted by the B tree. So all of the node stuff is all internal, so we can do whatever we want with those. And that's why I kind of made them package private. Didn't put a public or private here. That way we had the ability to unit test it at least. So if we take a look at the B tree again, if you just pass it the degrees, it'll pass a null comparator and the other degrees to the other constructor. We subtract 1 for the maximum keys. And if the comparator is null, we basically just use the natural order comparator, which basically assumes that the items that you're putting in here, which is a key, a K, is going to be some comparable of that object. So for example, you can use this on integers or strings because all of those classes are comparables of other integers. So that way I can actually use this comparator for determining the order, because it's very important that B trees and B plus trees are ordered. And then the root is basically a leaf node at this point. It just doesn't have any keys at that point. So then whenever we add a key, so let's come back to our example here. Let's just go with 1. Whenever we add a key, that's just going to stay within the leaf node. But right now it is a leaf node. And if we take a look at that add, we're getting a location. So a location is basically which index would this key most likely exist in. So if we take a look through this, we can basically grab the key count, iterate through basically like a binary search, trying to figure out where that key would exist, and it returns the index specifying that. It makes more sense with the internal nodes, because if you remember from the internal nodes, if we have children, the location of 1 would be index 0, and then it would be able to handle it that way. But if it's looking for key of 5, which doesn't exist in here, but if it was looking for 5, it would find the location as 1, because it would most likely be the first or the second, index 1, the second child of the children array, and then traverse down that. And then whenever it gets down to this leaf node, it finds the location as being 3, and then it does the comparison and realizes that, well, we don't even have an index 3, so it's not going to be in this collection, and it's going to return false. But get location is very important. I think we might have a get location here as well, which is similar, but like I said, it has to look at the children on this, whereas the leaf node only has to look at keys. All right, so then let's look at the part where it's going to break it up. So it finds the location, and then it adds the key at the given location and returns the superclass call to add, which is going to be up here in node. And this just checks to see if whenever we added that item, is it overflowing? Because let me refresh this again. And if we take a look at the animation, this is a degree of 3, so it's only going to have a maximum of 2 records in there. But we add that, and then we add a 3. Notice that it added it to that leaf node, and because it was overflowing, it decided to go ahead and split that record. And if you look at this, if it's overflow, it's going to call the split method, which of course the split on an internal node is going to be different than the leaf node. And we'll get to that here in a little bit. And we know that if we're splitting, it'll always result in an internal node as the new replacement. So then it adds the first key as the keys, and then the children, it adds this node because we're splitting it, and we're adding the sibling node, which is the one from the split, as the second child, and we're returning the new node from the add. So then the caller of that will know if it's non-null. We know that it was split, and we just reassign the root to that new node. So it basically, if add returns a non-null value, we will know that there was a split involved, and we have to restructure the tree. Same thing with the internal node. If we go to the add method in here, wherever that's at, we grab the other location, we grab the child at that location, and then we add the key to that child. And if the child, which could be an internal node or a leaf node, if it returns a non-null value, then we would have to merge that particular child. And that's the case here, where if I add a 4, it's going to return a new node, and it's going to have to merge that node with the current one. So if we look at that, we just make sure that the child node is an instance of internal node. It shouldn't ever not be. But then we are able to grab the keys from that and add them to the current, because we're merging it and basically throwing away this particular new child. And that's about it. Pretty simple. So all of this does work. I did create an extra class in here for GraphViz. If you've ever played around with GraphViz, it's really cool. You can basically do stuff like A to B, and it'll be able to generate a diagram of A to B, or B to C. And we can also do like A to C, for example. And that will be able to create the other diagram, which is very nice. So I basically have this GraphViz outputter. It just builds a string for the entire B tree information that it has on there, which is very nice, because then we would be able to do stuff in our unit test to be able to debug. So let's say, I haven't really talked about the unit test yet, but I am going to put some different number here, because what I did was I'm using parameterized tests. So I'm able to basically create a stream of arguments that are going to go through the parameterized values. And I created a method down here for testing the add. It's providing it with the degrees, a list of keys to add to the other tree, and what the expected tree is going to look like. And I created my own T node just to be an easier way to create a tree structure. And then I instantiate the other tree. I add all of the keys that are passed in. And then I have a try catch with the assertion error. But if there was an assertion problem, I debug with GraphViz, which does a couple of things. It'll be able to grab the GraphViz content, print it to the standard out, but I'm also throwing it onto the system clipboard using the AWT magic. So if we were to run this, I did produce a failure. because I did change one of these values. Which one was it? I probably should have paid more attention to that. I think it was this one right here. I changed it to 23. But because it was put into our clipboard, I can come over here and just paste it in and actually see the tree that was created with that B tree. And we can tell that this particular one has 7 and 89 in that one. And I was quote unquote expecting 7 and 23. So if I change that to 89, we'll be able to see that succeed now, because we are basically looking, see if I can do this in a way that I can see both of these. Let me move this here and move this over here. So the way I created my internal testing tree, I basically have this T node of integer, and I specify which keys are going to be at this node, and then I have the children, and I use a builder pattern similar to Domino UI to be able to add the other children. And this child will have a child with 1, 3, and 5 as the keys, and then I create more children, which for convenience, I created a leaf method that is able to create a new child node as a leaf. So -50, -5, 1, 2, and so on. So this basically creates this entire structure. And then whenever I compare, I basically just run through the combination of this node, which should be parameterized, right? With T. And this is going to be node of T. There we go. I modified a bunch of stuff earlier this morning to break all of these out into top level classes. And because they were internal classes, non-static, I had to change a bunch of stuff. But that does look like it works. So then the compare basically takes that root node from the tree and compares with this expected structure, making sure that the keys equal to the root keys. If not, it just returns false. Should probably put some extra logging in here. Maybe I should do a little bit more with throwing an assertion error. That way I have a full trace of where did it fail in the tree structure. But then I grab the children, and for each one of those, I just make sure that the sizes are the same. And for each child, I recursively call the compare with the children and what the expected child was going to be. And if any of those differ, I just return false. Otherwise, if I get down here, they must have been completely equal recursively down the tree chain. So that one's pretty simple. And that is my unit test for testing these tree structures, which is pretty nice. I like it so far. So before I started the stream, let me just rerun this to make sure that all is well. All right. I created another one for testing to remove data. So in here, I'm passing the arguments of the degrees. I actually did test one with larger number of degrees, which was 1,000. And I just added a bunch of numbers and made sure that I only had a single node. Should probably test my tests, making sure that the compare is correct. But this one does make sure that all of those items are in a single leaf node, and it doesn't actually do any kind of splitting, which makes a lot of sense. Where's the remove? All right, so here, testing remove, I pass it the degrees, the keys, like the entire set of keys that we're going to have in this tree, what the tree should look like before, a collection of keys that I want to remove, and what I'm expecting the tree to look like after that remove. So here we create a B tree with that number of degrees, add all of the keys, I compare, and then I basically debug any kind of assertion errors, rethrow the exception. Then assuming that the trees match what I was expecting, then it'll remove all of the keys that I provided. And then I do the exact same test on that same tree to make sure that it still looks the way I was expecting, even after the removal. So let's go ahead and add some arguments here for the remove data. Here it is. So args add arguments of, and let me just refresh my memory. It was degrees. So let's just do 4, because that's, I don't know why, but I've been testing with 4. The keys that I wanted to add, that is going to be that. What the tree is going to look like before. The keys that I want to remove, and then what the tree should look like after the removal. So let's go ahead and create some sort of scenario in this visualizer. All right, so we've added 1, 2, 3, and 4. Let's go ahead and add 5. Oh, this is the wrong degrees. I need to redo that. It's like, why isn't that allowing more objects in there? And I'm going to speed up this animation because it takes a little bit to enter these values if I'm waiting for that animation to come back. 6. All right. Yeah, that may be a little more complicated than I want to do. Let's just start out with a single node. 1, 2, and 3, right? Oh, wait. Did it again. 1, 2, 3. And that's what it should look like. 1, 2, 3. And in this node, it's just going to have keys 1, 2, 3. And this order does matter. And that's the nice thing about this. I'll show that here in a second. And then let's remove 2. Now we're going to have keys with 1 and 3. Oops, I don't know why I'm refreshing that. Yeah, that is not running all the tests. Well, let's make sure that we're running all the tests. I could probably just do the remove since we already did the add, but I just want to make sure that none of the other tests fail while I'm modifying the data. So I should probably run the entire unit test, but that one was successful. So if we come up here and we pass these in a different order, if I put like the 2 after that, it's still going to return a T node or B tree with all of the keys in an order. So you can see that's successful. If I were to expect it to put in the wrong order for some reason, which this will never happen, I can at least show that it fails. There we go. And because of it failing, I was able to paste in the diagram that it created of what it actually generated. So it's really nice for troubleshooting. So we have a single leaf node and we have 1, 2, 3, not 1, 3, 2. There we go. Yes, as singleton list. Singleton list. That's probably what I was complaining about. So if I run that, that should be successful now. There we go. Oh, nice. I can collapse that. I like parameterized tests. They're actually pretty nice because each one of these calls to that same method gets put down here into the other tree structure, and you can just collapse it if you don't want to see individual tests. So that works out pretty well. Let's get rid of that. So now back to our tree visualization. 1, 2, 3, 4. Let's go ahead and do this one. So args.add arguments of, I know that I have the ability to return a stream of, giving it a bunch of arguments, but I might want to do like loops and stuff in here. I wasn't sure what I was going to have in my test data creation. So in case I needed to do something complicated, I just used an array list. All right, so 4 arrays as list, 1, 2, 3, 4. New T node of integer. This is going to have the keys, just 3. And it's going to have 2 leaf nodes. The first leaf node is going to have a 1 and a 2, and we're going to have 3 and a 4. And singleton list. Let's remove the 2. So in this particular case, we are expecting the result to look like this. Because after we had a structure that looked like this, we remove the 2 and it will result in that. And that should still be successful because the leaf node should be removing correctly, and it does. All right. So I'm just going to copy and paste this because now we're going to also remove, well, let's instead of 2, let's do 3. So then that removes that. Let's just make sure that still works before testing the next one. Oh, that did not work. Oh, it's because it had to, because 3 was no longer there, it actually had to remove that key from the parent node as well. That makes a lot of sense. So let's take a look at how it did that first. So if we remove, grab the location of where we need to remove from, and this is the leaf node, so we're really testing just the leaf. If the location, I guess I could unit test these classes individually. Didn't even think of that. Probably would have made it a little bit easier. Oh well, I might do that later. So we grab the location of the key, and basically this is just determining whether or not, basically where that key should be based upon the keys that it already has in the collection. So if the location is greater than or equal to the key count, which means that it's in a location. So if we have 1 and 2 and it's looking for 3, it's going to give us a location outside of how many keys that we have. Or if if it's not greater than the key count, then we look at the keys that we currently have at that location and then do the comparator comparison. And if they're not equal, and that is basically just calling the comparator compare on both of those, and an equal equals 0, just to make sure that they're equal. Obviously, I should probably inverse that. Not equal. Not equal. Because that's a little bit easier to look at. So if they're not equal, should it be NEQ? I don't know. Then we're going to return false because it was unable to remove it because it's either not in this leaf node or the item in that location that it should be is not equal to that key that we're trying to remove. So obviously that would be false. But if neither one of those conditions are correct, then we go ahead and remove that location because we're using the index because we did find out that it was equal. So we do remove that index. And then if we determine that the keys is empty, then we have to do some stuff, which we haven't figured out yet because obviously I haven't been doing that. So what would be the stuff that we have to do? Well, let's just use our current example. In our current example, 4 is not, this one's not empty, so won't even get there. And this returns true, which will go up to the internal node because we're in here and we're just making sure that the remove can work in the other child. So let's find the remove method in the internal. So this one's a little bit more complicated. So here we grab the other location, which 3 in this particular case was index 1. This one, we just make sure that the child at that location key count is, oh wait, before we get to that, we just call the other remove on the other child. And that just goes through the other code that we just looked at. So that provides a true or false result. Then we just check to see if the key count of that child is now 0, which it's not. So we're just going to ignore this one. We're just going to put a breakpoint there just because we're going to look at that logic later. So if the location is not 0 and the keys at location -1 is not equal to the first leaf key, which it wouldn't be because of it removing the 3, that's no longer the case because this is a 4. And one of the rules for the B tree is that the key here is going to be the first key in the child, the corresponding child. So here you see the other 3, that's the first key here. 5, first key here. So if we were to remove 5 from here and the first key ends up being 6, we need to replace this key with 6. So in that particular case, we set that key to the first leaf key in that child. So this is where it set it to 4. So that makes a lot of sense. So then if the child still has keys because the key count is greater than 0, we just return that result to the other parent. And I don't think the B tree does anything. No, it just returns that. So in that particular case, we know that we have no, that's the wrong place. We have a 4 as the parent, or the internal key, or the internal node's key. It's going to be 4 because it's the first child of this one. So now if we rerun that, it should be successful. All right. So now what we want to do, let's remove the 4 as well. Oops, not a singleton list, but arrays as list 3 and 4. So now we're removing 3 and 4. So if we go back to this visualization and we want to remove 3, notice that it did 4 in the parent. Then we want to remove 4. It should split the nodes. So let's look at that again. Oh, yeah. Now that the tree is in a different order, and we deleted 3 first. Let's slow down this animation. And now whenever we delete the 4, it tries to find the 4. It deletes it. This is empty. So then it shifts this stuff over, and then it has to change this key to the first leaf key, the first key of this leaf. Yeah, that's confusing, but that makes a lot of sense. So it does split that one and pulls, like shifts over into the other one. So that's the one that we got to figure out. Because at the end of it, we should have 2 as the key, and we should have a leaf with 1 and a leaf with 2. So we have a 2 as a key here, and then a child leaf 1 and a child leaf 2. So this is what it should end up as, but I'm pretty sure that this is not what it's going to be. And we actually got an exception, so that does mean that I haven't implemented that yet. So let's take a look at the leaf node first. What happens whenever the keys is empty? So in this particular case, what did it do? It basically deleted itself. But I think it has to fix the linked list part, because if we're going to be deleting this node, we're basically needing to, I don't have anything for this. Let's create a little diagram here. I've never used this tool. This is the new one with Apple. It's not very convenient, but it'll work for these purposes. All right, so if I started out with one and 2 here, and this one's 4, and this one's 4. Okay. And let's create some arrows here. And if you take a look at the link code, in the leaf, we have the ability to link them, which, how am I doing that? I keep track of the next and the previous, so I'm doing a double link list instead of just a single link list. That way, if I need to do like a less than iteration, I would be able to use that double link list to go to the previous nodes as well, and that wasn't that difficult to create. All right, so let's see where these are actually done. So it does look like I have in merge. Where else am I doing this? Then remove. Split. Okay. So this is whenever it splits. I didn't really go through this code. I guess I forgot to. So whenever we're adding, we gotta come back here. Whenever we add another item. Oh, I need to change that the speed of the animation back. That's fine. It's going to split this very next one. So whenever I insert this, basically what it's going to do is figure out which node that it needs to put it in. It puts it in there, but then it's like, hey, our maximum degree is 4, so we're overflowing, and it needs to split this. So the split code is basically creating a new leaf, which is going to be the sibling node. It's going to create a new node over here. It grabs the key count, the current key count, because we've already added it to this node. So can I pause that? Yeah, I can pause it, but I would have to do this quickly. So if I insert here, so I paused it. Oh, I can do this step by step. That's kind of cool too. And that was because in this add, nope. Where's it actually doing the add? So in the internal node, whenever it calls add, it's just adding the key. I swore that the leaf node did that as well. Yeah, it does. It's kind of weird. So it does do the add, and then in the internal node, where is that done? Oh, okay. So in the superclass, then it checks to see if it's overflow. In this particular case, it is overflow, so it's going to call split. And I pulled this way up into the node class because this is a common behavior for both internal nodes overflowing as well as leaf nodes overflowing. It'll need to split, and what it does at that point, step forward. Wow, it does it all in the same step. Oops, I did not mean to skip back. I meant to do a step back. All right, so step forward, it adds it. So then what I want to do is split off these two into their own node. And these two are just staying in the current node. So it creates a, it does the split, which creates the new leaf node, and it grabs the second half. So it gets the key count divided by 2 to the key count, and we create a sublist of our keys to that. I guess I can pull that sublist out, but then it adds all of those keys to the new node, and then it clears those keys out of the current node. And then I maintain the linked list part, which the new node, which is our sibling node. I should probably rename this to B-less. New sibling node. All right, so the new sibling node, the next one is going to be this next one's previous next one. Yeah, that doesn't make a lot of sense, but it's basically moving what I currently had as my next node. Because we're splitting it, I'm moving that next to my sibling, and it's able to continue that chain. And the sibling's previous is going to be this, and then I'm setting this dot next to the new sibling node, so that maintains the dual link. The dual linking list, both directions. I'm able to get to the next sibling node through this next, and then the next sibling node's next is my previous next. Yeah. and vice versa with the other previous. All right, so that should make a lot of sense. Step forward. So now we need to be able to pull that key up. So after it did the split, here it's creating a new internal node, and it's just delegating the comparator and the other maximum keys to that internal node. I'm adding the first leaf key as the new nodes, new root nodes keys. I'm adding this as the left sibling and adding the new sibling from that split to the right child, and then I return the new root. But unfortunately, that creates a new root. So let's come over here. I'm looking at split again. Let's ignore that. Why am I looking at split? We were looking at remove. So whenever we remove, yeah, I think I confused a bunch of stuff. All right, so let's start over on this. Yeah, I know. All the academic stuff can be difficult. So speed that up. 3, 4, and we deleted 3. All right, so we're going to delete 4. All right. So the way we delete 4 or remove 4, we come all the way down here into the oh, that's why we were talking about the splitting, because we have the double linked list. So if we were to assume that there was an imaginary leaf node over here, there's not, but right now it's null. But if it did exist, what we have to do is change this pointer from here to over there so that it would just bypass this node, right? So that's what I'm doing there. So if the keys is empty, we need to maintain double link list. So if the next is not null, and in this particular case, if it's not null, it has to do, oops, the previous, because this is a double link list. Let's go ahead and copy these so that we can see all of these. So assuming this is the case, hopefully this is showing up, yeah. So what we have to do is, assuming that the next is non-null, we have to go to the next previous, which is this one, and change it from this to our previous. And that's what that does. And once that's done, then we need to change our previous. If previous, I guess I started doing that. If the previous is not null, then we need to go to the previous next and assign it to our next. So then it changes those connections. And that maintains the double link list for forwards and back. And that's going to return true, that it was able to remove it. So then we are back to the internal node for that removal, right? So that has the other result. So in that particular case, now the key count is 0. So what we need to do is remove that child from the other location and the key that was associated with it, right? No, that's not good. No, that should be correct. So that's actually going to remove this child loop that no longer exists. Obviously, those no longer exist. And that child no longer exists. I mean, I'm assuming that in this example that this was a child from somewhere else. Just ignore that. And then it removes the other key. So now this is blank. All right. So then we go down to this. So if the location is not 0, this one, it actually is 0 because it was the only location. No, it was 1. Okay, so if it's 1, well, that one's going to throw a index out of bounds exception. That's where we got that. Okay, so this is where we have the index out of bounds exception. So I guess we need to do a little bit more if the children count as 0. I think we have to combine these into an if else, because we can't ever execute this logic if the key count of that child is 0. Yeah, and because we removed it, this isn't going to make sense anymore either. All right. Oh boy. Let's pull that out. So in this particular case, because of the fact that we're removing that child, we weren't able to call children to get on it again. So we might as well just hold it. So if the original child count is greater than 0, we know that it didn't go in here, which we're returning the result anyway. So I guess that doesn't really matter. So if the child, I guess that doesn't make any sense. Why did I do it like that? Because we're returning the result and not even getting to this other stuff. So I guess I don't need to worry about that. Wait, why were we getting a index out of bounds exception then? Maybe that's in a different spot. No. Keys.remove location. Oh yeah, that's right. -1. Right? No, that doesn't make any sense. Why am I removing that? Because we're assuming, because of rules, if the child no longer has keys, the current key disappears. Okay, so that's removing location -1, because that's how we're basically getting to it anyways. Because like looking at this graph, if we take a look at this, I'm using the records in here. So the shape of a record, I'm using these little imaginary positions for doing all of the different associations. So these, the F0, F1, F2, those are going to be the children indexes. So this is child index 0, child index 1. But for keys, it has an array of a single element. So the keys is always going to be one less. The size is going to be one less than the number of children. Unless it's a leaf node, then each one of these, it doesn't really matter because those don't actually exist in the other leaf nodes, which I should probably render them a little differently, but not to worry about that right now. This one does exist because of the double link. So this one's the next, and this one's previous, and this one's next and it's null, and this one's previous and it's null. But for the internal nodes, again, keys size will always be one less than the children size. So if we're removing child at index 1, we will want to remove key at index 1 minus 1, which would be index 0, which would be removing that 4. So that gets rid of that key, and then we just return the result. So now we get down here, we know that the keys that we remove the other child. No, we need to do more stuff here, unfortunately. We can't just leave it at that, right? We need to do more. So if the child is empty, which this one would be empty, then we need to not only remove that child and that key, but then we're going to have to shift things around because now we're empty. So if I were to paste what we have now, see, it's empty. Let me undo that so we can get the previous one back. All right, so here's where we're having the issue. So I'm wondering why I returned the other result there. So I'm going to remove that. We need to do more stuff. So this one would have to be an else if. So now if the child count is greater than 0, then we just return the result because nothing else needs to be done. But because of the fact that we have 0 children as the key count, then we need to do some shifting around. So what does that look like now that I've changed it to that? Another index out of bounds exception, which makes sense. So if the location is not 0, I'm not sure what I was thinking here. In this particular case, it's not 0, it's 1. And children get location -1 key count is greater than the max keys +1 divided by 2. So 4 + 1 divided by 2. That's basically the degrees. So that's 4, because the max keys in this particular case is 3. But 4 divided by 2, which is 2. So we're just checking to see if the children over here is greater than half of the maximum keys available. So this doesn't actually execute, does it? Can I rerun this debug? Yeah. Yeah, I didn't think so. All right, so The key that we're deleting now is 4. So that's not true. So if the location is not equal to the key count, which the current key count is going to be 0, so that's not correct. So what did we do here? Slow animation. Go in there. Remove that. I want to step forward, but I don't want to. Okay, so then it shifts everything because it's empty. I'm curious of how much it does. So let's change the maximum degree to 6. 1. Oh, let's speed up that animation. Yeah, probably don't need to do that. So if we do delete of 7, delete of, well, 8 doesn't exist. Or wait. Maximum degree of 6. Shouldn't that have grown further? So maximum degree, that means that 5 keys maximum in here. So if I deleted 7, 8, 9, 10. Oh, wait, what? Wasn't paying attention. What just happened? Interesting. So it's more to it than, oh boy. So let's take a look at the Wikipedia page. Deletion. The purpose of the delete algorithm is to remove the desired entry node from the tree structure. Recursively call the delete algorithm on the appropriate node until node is found. For each function call, we traverse along using the index to navigate until we find the node, remove it, and then work our way back up to the other root. All right, so if L is at least half full, we're done. Okay, so this is looking at half full. So if we remove 9, this is no longer half full, right? Well, it didn't do anything. Let me go back to this. So if we remove 4, we remove 5, because this is maximum degree of 6. So the maximum number of keys, and maybe this is a bad example because let's switch this to 5 to make it a little bit easier. Because this one will allow 4 keys, but then as soon as you get the 5th one in here, then it does its split. I'm kind of curious, does ours do this too? All right, so let me do that. And let's go over to our add data. Let's add this example in here too. Args add arguments of, and maximum degree is 5. One, two, three, four, 5. This is going to have keys of 1 and 2, no children. Then we're going to have another child in here. And this is going to have keys 3, 4, and 5, right? Does that still bode well? Yeah. I don't need breakpoints right now. All right, so yeah, that worked. So the test for this one was for 5, 1, 2, 3, 4, 5, and it has this. I didn't do anything with the other 2 string, but it's printing out the arguments that we had on that test, and that was successful. So it did create that correctly. All right, so that's good. Let's go back to our remove. Let's delete 3. So we already know that that one worked. Delete 4, and yeah, step back. If we delete 4, what's it making the decision on? So 5 maximum degrees. 5 divided by 2, which is 3. Or, so this is maximum nodes of, let me go back one more. Nope. 0 to 5. All right. Maximum degree. So maximum nodes is 4. So max keys divided by 2. So that's basically saying that the minimum has to be 2. So here, whenever we delete 4, it's like there's no minimum of 2 anymore. Okay. So that should never actually occur if we do this correctly. Right? So if I skip back. So the leaf node, have you been seeing this? Or was this completely off the screen? That may have been completely off the screen. My mistake. So yeah, whenever we delete the 4, it's going to be like, hey, there's less than half of the maximum keys. It needs to shift things around. And the way it does that comes down here, goes to delete 4. It does delete 4. It that was interesting. The animation on that was pretty interesting. Because it deleted the node and then it set 5 up here. Right here. And then this is less than half of the expected nodes, which would be 2. So what this does borrows from sibling after redistribution. Ah, I get it. Where did that go? So basically I should probably have a 3 in here. Let me just play through that. Let me skip back. If I add a 3, it should add it to the left side. Right. So now if I delete the 4, it's going to shift the 3 into this side. It's going to borrow from its predecessor. And because this node is at least half of the maximum keys, it didn't have to collapse. Okay, that makes sense. Ooh. So this will never be empty. We're gonna have to figure that one out. Let's get back. So what we want to do here is if we remove that, parent's gonna have to check the child node count, and it's gonna have to tell the child to pillage its neighbor. Let me think about that for a little bit. I'm going to take a quick 10-minute break. Whenever we come back, I'm going to see if we can get further along with this remove. This one, I'm going to have to figure out whose responsibility is it to do the shifting around. Where did that go? That was not what I wanted to open, because we need to basically be able to borrow from its predecessor. And this one will take place. But we should only borrow from the predecessor if the predecessor has the max keys divided by 2, half of the other keys allowed. Yeah, so let me take a 10-minute break and I will be right back. Yeah, I'm a couple of seconds early, but I wanted to jump back into this. So just looking at the the different steps with this, whenever I remove the 4 and then I step forward, it says node has too few keys, stealing from left sibling. So it's able to steal from here. Then whenever it goes up to the other parent, it changes the first node. So on the leaf node, this is no longer going to be the case. It's not going to be empty, because from here we're going to have to steal from the previous. Yeah, there's different scenarios that we need to figure out. So if keys size is less than max keys divided by 2, right, let's just put a breakpoint there. Null pointer exception. Oh wait, it's only because of the evaluation here. That's fine. So here we have the max keys 3. We're removing 4. Should probably look at this example first. So let's change our example to match. I was just adding 1, 2, 3, 4, 5. Is that right? And this is max degree 5, 2, 3, 4, 5. We already tested that one, right? Yeah, 1, 2, 3, 4, 5. We have 3 is the root, 1, 2 on the left, 3, 4, 5 is right. Correct. How did I create that before? Because it's looking different than what I had before. Delete 3. Add 3. There we go. Because I wanted that 3 on that side. So if I inserted 1, 2, 4, 5, 6, delete 6, insert 3. Yeah, that's really stupid. How do I do this otherwise? Because I want to start out with a collection. Seven. Yeah, I don't want to do that either because that's busting up. How can I do that? How can I do that? 1, 5, 6, 7, 8. Now I add 3. That could work. So 1, 5, 6, 7, 8. Which ones succeed here? First 2 succeed. All right, so I'm going to comment this one out for now. So we are degree of 5. We are doing 1, 2, no, 1, and then 5, 6, 7, 8. 5, 6, 7, 8. And then we add 3. It should come up with this, right? So this should be a 6. 1, 3, 5 on the left. And 6, 7, 8 on the right. Let's just make sure that's what we got. Which part of that? I should have probably identified where in that test. Okay, so this is after the removal. So yeah, that's correct. All right. So let's remove 6. We're going to repeat this one because it'll probably be a little bit easier to repeat this for every step. So here we're going to remove 6. Remove 6. All right. That should succeed. No, it did not. What did our tree look like? Oh yeah, I forgot to change the other root. Duh. Because we removed the 6. All right, let's run that again. All right, that time it succeeded. All right, so now we want to do the same thing, but instead of this, we want to remove the 6 and the 7, because if we delete the 7, that has to borrow from its previous, or yeah, let's change the animation screen to a little bit slower. So we locate it, we delete that, we borrow, adjust, and that's it. Okay. So it should result in this being 5, and the 5 is moved down here. All right, so hopefully this works. Well, obviously it's not going to work because we haven't written that part yet. I just want to see what that graph looks like before we change anything. All right, so we will need to do our borrowing. Less than or equal. Max keys divided by 2. Oh wait, I'm skipping breakpoints. Duh. It's like, why didn't it get there? I skipped breakpoints. All right. So here the keys size is less than the max keys divided by 2. Because we're left with 1. So now we need to borrow from previous borrow. Oh, see, and that's the thing, like, which way do we borrow? Because what if we're not in the same, what if we're not from the same tree? Ooh, it's annoying. Because what if there's like a separation of here? Let me change that. Let's just start adding numbers again. All right, so let's keep going. Not enough numbers. One more. Nope, one more. There we go. All right, so what if we are down here and we remove the 7? Are we gonna borrow the 6? Can't really do that because it's on a different path. Yeah, we could. So in this particular case, if we delete 7, now this is a bad example because of the fact I just need a way to enter these numbers faster. Because every time I enter a number and insert, I mean, I can hit enter and it'll insert, but it loses focus. It doesn't refocus that field, so then I end up having to click in it to add the next number. All right, so let's just do this by hand until we have at least 3 levels. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. All right, so here we go. So let's pause this and let's delete 7 this time. All right, so deleting 7. Step forward. It's locating it. Locating it. Locating it. Found it. Merging nodes. So when does it know to merge versus borrow? To redistribute. Okay, so let's look at this again. I'm not entirely sure what L is. What is L? The purpose of the delete algorithm is to remove the desired node entry or desired entry node from the tree structure. We recursively call the delete blah 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 blah. All right. So at entry L that we wish to remove. $10, 50, 51, 60, 50, 51, 60. So this one borrowed. If L is at least half full, we're done. So in that particular case, this one's not half full anymore. If it were, it would just remove it and we'll be done, but it's not. So if L has only D minus 1 entries, and I'm not sure what D is, degrees. So that's the maximum keys. So D minus 1 is maximum keys because it's the degree is minus 1 is the maximum keys. So if L has only the maximum key entries, what? Yeah, it has to be within the same parent. That makes sense. So this one's, if redistributing fails, then it needs to merge L and the other sibling. So how do we know if we're within the same parent? I guess that would have to be the parent that makes that decision, right? So in this particular case, we probably can't do this. We probably just need to do that. Right? So then, and it's up to the parent to make that determination. So we know at an internal node, because all of the leaf nodes are going to be at the same level. We're not going to have an internal node that has a mix of internal nodes and leaf nodes as children. So if one's a leaf, they're all leaves. And same with internals. So if it's one's an internal leaf, they're all internal leaves as the other children. So those are some ground rules for some of this. So then we remove the child, we grab the result. See, this one was taking the assumption that we were going down to 0, and that's not the case. We're wanting to check to see if it's the degrees divided by 2. Nothing was removed, then we don't have to do anything. I could just do it like this. If not. If nothing was removed, we can just return false there. All right, so now that we did remove it, let's just go back here. Step back. So we did remove it. Now we need to check the child at that location. For the child count. That's that guy right there. So this is the child key count after the removal, which will return 1. I'm gonna ignore that one. If the location is not 0, meaning that if it were 0, we would be removing the same key that was here. But if it's not, no, if it's not 0, what does the 0 have anything to do with it? I know that we defined this earlier, but my mind's already drawn a blank on it. All right, so the location in this particular case, it is 0, right? Because the location is that, and we're getting the child at that location at 0. That makes me think that it should be a location. I'm just going to comment all that out. Oh, I think this was my original logic. That might actually be correct. Let me look at that logic again. Let me split the screen so I can see it. Let's go ahead and come back up here. All right, so we grab the that. Here I'm just returning. I'm just short-circuiting because it's pointless to do any of this stuff if we didn't actually delete anything. So it might make sense to do that. Well, let's yeah, let's just remove that. All right, let's see what this does. So if we do remove a child and the location is not 0 and the children at that location first leaf key compared to this key -1. If that's not the same, let's not equal, because we want to use the comparator that we set. They're not equal. Then we set the the key at location -1. And that's why we can't do location 0. That makes sense, because this will always be the key is going to match the first key in the non-first child. All right, then we grab the children at that location, which is going to be 1 or 0 in this particular case. And if it is less than half full, that'll be true here. If it's not the first location, this one it is, so we can't do that. So if the location is not equal to key count, which means that it would be the very last one, that one's not the case. So here we want, if the location is 0, we need to merge 0. All right, let's take a look at the merge. If they are leaf nodes, oh, okay. So apparently I did some of this already. I just didn't have the logic right on the other parent. All right, so here we're going to merge this guy into here. See, that might be a little confusing though, because what if, so what would happen if I were to, I'm just trying to think this through, because if I merge this, would there be a possibility of this one overflowing? Is that a possibility of it overflowing? Maybe not. So let's say we're going to, let's just go through this one example and we'll try to come up with some sort of example that would cause the other problem. So let's merge, and this is an internal node. So if the child at that location is an instance of leaf node, which it is, we're only going to be looking at it from this perspective. We're merging the left node, which is the location, and the right node. Let me just double check that. So location is 0. So we intend for it to always merge with the right location. Okay. And we know that we won't get in there if the location is the key count, which is basically if the location is 1, which means, or 2 in this particular case, index 2 is this one, so we can't merge it with the right because that doesn't exist. So that's fine. So we're going to merge. Left node is going to be the location. Right node is the location plus 1. And we're taking the left node keys and we're adding all of the ones to the right. So we're actually merging from the right to the left. And we're removing the children to the right. I mean, I think it did that a little different. I don't think it really matters. Step back. So we're taking all of the keys from the right node, throwing them into the left node. And because we're doing an add all, it's going to do them in the same order. And this is an array list, right? Should be. Keys, array list. So yeah, it's going to add all of them in order. So that probably makes more sense to do it that way because of the order maintenance. All right, so then the left node next. The left node next will need to follow the right nodes next. Yep. And then the right node, the new right node, or no. Right node next previous. Right node, this one. Next previous, yeah. Has to be the left node. Yeah, so it's basically, because this visualization doesn't show the left navigation. So we basically have to go to the right nodes next, which is going to be this node. Its previous has to be the left node. And then we remove that child. That's merging those two together. Okay. All right. Ooh. Oh boy. And this is a different example, but wait, did that fix our problem? So I'm going to pause breakpoints and let's go ahead and execute that again and see what we have. All right, so it still has an error. Cannot assign field previous because right node next is null. Yeah, I should probably take a look at the example here. Back to the example that we're currently working on. I should probably redo that one. All right, so max degree is 5. And we're adding 1, 5, 6, 7, 8, and then 3. 1, 5, 6, 7, 8, and 3. Has 6, 1, 3, 5, 6, 1, 3, 5, 6, 7, 8, 6, 7, 8. All right. So then we're removing 6 and 7. 6, 7. Step back. I'm going to pause and I'm going to delete 7. So now it's deleting 7. It's Step forward, it's locating, deleting it. Node has too few keys, so it's stealing from the left sibling. Okay, so I think it's one of these. So if I were to pull that back in, so we're not merging in this particular example. So we'll have to come up with an example that we merge. So we're doing a left shift. Step back. So we're doing a left shift. So let's take a look at left shift. That shouldn't happen. Step into. So the children, these are both leaf nodes. So this is going to fail with the class cast exception, right? Is that the exception that? Yeah, class cast exception. Okay, so we did get a class cast exception. Good. That is good. All right, so I guess I did merge, but not left shift. So if, where's my merge? Children get location instance of leaf node, then we do that. Otherwise we do this. Obviously we're going to have to test these at some point. Assuming that they are internal nodes, what are we doing here? So we're grabbing the left node, and the right node. So same thing here, but instead of internal nodes, these are going to be leaf node. All right. So this is only shifting at a single value. I guess that's okay. Right node. Do we need to do anything? Oh, obviously, because of leaf nodes, we don't have children. Yeah, this is shifting the children. Well, let's just get this to work. So right node, because I think I can do this without having to have the specifics here. Right node, this doesn't have children. because we're doing this in the other parent. So then keys.set location -1 to left node keys. Remove node get key count is 1. The very last one. Does that make sense? I don't know if that makes sense or not. My mind's kind of hurting right now. So we have the left node and the right node. So we're left shift. I think the name of this method is throwing me off because we're actually shifting from the left to the right, right? So I should probably do like borrow left. So then right node keys, add, basically inserting as the first one in this collection. That doesn't make any sense. So how is it doing it down here? What was the intent of this method? It's been a week since I wrote this. So if they're just all internal nodes, we are grabbing the children to the left, children at the current, the right node keys, adding, we're inserting that key that doesn't make any sense. Let's delete all that. Okay, apparently I can use yellow sticky notes. I'm just going to draw it like this. Obviously, this can have multiple children. Oh, I can't have anything in between. I did 4 here. This is 4, 5. Then oh, you're not seeing this. Over here, it would be like 8 and 9. And let's assume that these are internal nodes instead of leaf nodes. So whenever we're removing let's say that we're removing the 9 here. This is less than half full, so we want to borrow. So what we're doing is we're taking this guy, left node, right node, and we're how does that make any sense? Because we already have that here. That does, yeah, that doesn't make any sense. I don't think this is doing what I'm thinking it should be doing. Hmm. All right, so if the child that we're removing a key from is all of the sudden less than half, which if I did that, it's less than half. Then I check to see if the location is not 0 and the child before it is greater than half. Then it does a left shift, but that's not actually doing a left shift. That would be shifting from the left to the right. It's like right shift. I think these are named backwards. Otherwise, if the location is not the last one and the children at the one after this one is greater than half, then we shift from this one to this one. Otherwise, if the location is 0, like if we were deleting here, then we need to merge. Otherwise, we merge to the location previous. Yes, that makes sense. But this left shift doesn't, it's not written right. So this is borrow left to right. I'm just going to rename it that. Borrow left to right. Or borrow from left because, yeah, borrow from left. Because that's exactly what we're trying to do, is borrow from the left. Because if we're borrowing from the left, so this one would take, actually, let's do a remove here, right? Yeah, I should probably do this in terms of leaf node. But I'm thinking in terms of leaf node. I need to figure out what to do with the other children. because we borrowed from the left, we have to reset the key to the first one here. So now we just have to figure out the other children. So if this had children below it before, we would have to move the last child as the first child here. So if the left node instance of internal node, so this should only happen if it's an internal node. We should do right node children add 0 left node children remove left node key count plus 1. And then we should be able to delete this stuff. Am I right? I must have messed something up. Or wait. So we should only set right node next previous if the right node next exists. All right. What do we have going on here? That is not right. I think I just messed something up royally. Bad thing about these sort of data structures is that you have to have in your head a state diagram and remember what state you're currently in. So this one we're shifting. Borrow from the left. And this only happens if the current node that we're deleting out of is less than half, and we have a node to the left and its key count is more than half. Because the children to the left at location -1 has 3 keys, which is more than half. We have 1, 3, and 5, so we're wanting to borrow the 5 to move over here. So step into that. See, if we're borrowing, we don't have to change the linked list. So that's a good thing. Grab the node to the left, node to the right, which is our current node. And the right node keys, we want to add the last node key. Let's hit play. Now, that died. Index out of bounds. Where did it have an index out of bounds? Oh, key count. -1. That's going to do the last one. All right, so the right node keys is 5 and 8. Left node keys is 1 and 3. 1 and 3, 5 and 8. That is correct. And this keys, we need to change that from 8 to 5 because it has to be the first one. That is what this line is going to do. So this key at 0 is 5. Yep. That's it. Yeah, and there's more stuff involved. That's right. Step forward. So we borrow, we set. Oh, that's it. So what was my problem here? Test data moved. Wanting to remove 6 and 7, so skip back. The 6 and the 7 skip back again. We have the 6. 6. Oh, play. And 7. We should have 5, 1, 3, 5, and 8. Yeah. And why isn't that what we have? Why is it like that? Where did the 4 come from? Or wait, is this a different? This is a different test. Which one's this? This is where we're passing in 4 and 1, 2, 3, 4. This one right here. So this one's failing. Why is this all of a sudden failing? All right, let's take this one into consideration. So we're doing maximum degree as 4. We're adding 1, 2, 3, 4 in order. We're making sure that 3, 1 and 2, 3 and 4, that's correct. And we're removing 2. Oh, it's because we changed that. See, that one's kind of interesting. Why does this one not care about being half? Because this is, so maximum degree minus 1 divided by 2, which would be 1, right? Are we even getting in here? I'm not sure what the test data is for this one. Which one is this? We're adding 1, 2, 3, 4. Degree of 4. Is that the one that we're wanting? Remove data. Here we go. So it's not this one. It's this one. So we're removing 2. Yeah. Remove keys. Yep. All right, so we're removing the other 2. And we come back over here. So we removed the 2, and the location key count is less than max keys, which is 3, right? Plus 1 divided by 2, which would be 2. Ah, okay. So that's the other problem. Maximum degrees. I wonder if this visualization is correct. Wonder if I should just do it like this. So maximum keys, which is 3 divided by 2. Might change that. Yeah, rerun that. That time it was successful. So I may have had that logic wrong. Okay. Whew. This is getting interesting. Okay. So now we have to figure out some more complex stuff because we're only looking at leaf nodes there. I kind of want to look at what would happen if I were to, well, let's try a shift right. How do we come up with a scenario that does that? So all of these are successful. All right, so if we were to borrow from the right, so let's start over. We're doing it with 5. Actually, let me clear that. Let's go with so that I can do things in between. 10, 20, 30, 40, 50, 60, 70, 80, 90. How do we borrow from the right? We can add a 35. That would add it here. Or wait, no, we're wanting to borrow from the right. So let's delete that 35. So if the location is not 0, well, let's say that it is 0. So let's delete the 10. There we go. So 10 through 90. Fifty, 70. And this will have 4 leaves. First one is going to be 10 and 20. Second leaf is going to be 30, 40. 50, 60, and 70, 80, right? All right, so this time we're wanting to delete singleton list of 10. So test-driven development. Oh, why do I always do that? I need to get rid of that. Extra pair in there. All right. So what is my tree supposed to look like after I delete a 10? 50 and 70. And then 20, 30, 40. 50, 60, 70, 80, 90. Oh, did I forget the 90 in here? How did I forget the 90? Step back. Okay, so 90 was in the final leaf node. So delete that 10 again, and that's what we should end up with. Let's cross our fingers and see. Nope. That one didn't work. Okay, cool. So what did we end up with? Yeah, that's wrong. Close, but wrong. Did we get a class cast exception? No, we did not. Okay. All right, so which one did that fall in? I'm assuming it was this one, right? No, it was not. I guess it was a merge. It wasn't borrowing. That's right. Looking at this, it merged. So we haven't really looked at the other merged ones yet. So if it is 0, we need to do that. Okay, so here's the issues. All right. We only know of the leaf node, but what if I were to do node of k left node is equal to children get that location, and then the other right node, the location plus 1. So we're merging. Let's get back. Let's 10. Step forward. So we delete 10. Now we need to merge the nodes. So which way was this wanting to merge? This was taking it was consolidating the right keys into the left node. Which makes sense because of maintaining order. So now, if left node, instance of leaf node, so what would we need to do with that? So if we're merging, we basically have to drop that key. So this.keys, remove that location. So that would remove that. And then this.children, remove location plus 1 because we're consolidating. Yep, that's what I did. I need to take all of the children from the right node, throw it into the left node. Or wait, it's not children, so that's fine. Left node, children, add all, right node, children. Seems correct. That can be done regardless of this being a leaf node or not, because children still exist, right? It's just going to be an empty list. So then it would be adding an empty list to an empty list. That's fine. All right. So that takes care of all of this, I believe. So now we just need to see if it's a leaf node, if the right node next all right, so we're merging these. I don't need to do anything with the other right node next, right? No, we're dropping the other right node. So we need to grab the right node next. So the left node next would have to be the right node's next. And the right node's next previous has to go to the left node. And I think that's done. I think that's done. Yeah. Yay. Yay. That actually worked. All right. So now if we come over here. Oh, wait, I didn't copy and paste that. That's fine. That's the old one. All right, so that one should work. Actually, in my unit test, in my remove test, I should probably just debug regardless. Oops, I don't know why I refreshed that. So this will just give me the last one in the system clipboard, and that's fine. So this is what it looked like after it removed 10. So let's just play. So we have 50, 70, 20, 30, 40, 20, 30, 40, 50, 60, 70, 80, 90. Whew. All right. Probably should execute this with, yeah, let's run these tests with, coverage. Let's see where we haven't covered. All right, so then internal node. Yeah, those breakpoints are pointless now. We haven't done the right shift, so we do need to figure out how to borrow from the right. Maybe that'll be our next one. And leaf node. If the location is greater than or equal to the key count. So basically we're removing the last key. Oh, wait, location is greater than the key count. That's right. Because if the location, because it's going to be the size. Or the keys are not equal. So basically in that particular case, we can test that one too. Basically if we're removing like 91, it would return this node. And it would return the index of 0, 1, 2, 3. And that's greater than the key count, so it would have to return false. I'm not sure how this would come about, where it returns 2, but they're not equal. I don't know how that would happen. But if that happened, then obviously we would return false because we didn't actually return or remove any keys. All right, so the next on the list, this is real fun. We need to try to borrow from the right. So I'm going to rename this one to borrow from right. And we're only borrowing a single item. When would that happen? If the location is not the key count, so we're not looking at the last one. So the location can't be the last child. And the next, because this is only happening if the current one is less than half. It's checking to see if the next one. Okay, so we look left first. That makes sense. So we look left first. And if that has more than half, then we borrow from left. But if it doesn't have more than half, and the right side, the right node has more than half, then we borrow from the right. Okay, so let's let me take a lunch break. Let me take a probably like a 20-minute lunch break. 10 minutes is just not long enough, but let me do that, and whenever we come back, we're going to write the code to borrow from the right. Just have to come up with the scenario for that. I will be right back. So where we left off was we need to be able to come up with something that can borrow from the right. So let's come up with a scenario where we have to borrow from the right. So the only time that would happen is if the current one that we just removed a key from is, excuse me, less than the less than half. And then, oops, forgot about my timer. Just reminding me to come back to the stream. So I might want to delete 30. So in this particular case, if I were to delete 60, that should borrow from the right, correct? All right, let's go ahead and add a test case for this. So it's basically going to be the same thing as this. Which keys did I delete? Skip back. Skip back. All right, so I deleted 10. Arrays as list. 10 and then 30, right? So 10. And then 30. And the next one, if I were to delete 60, that would borrow the 70 from this, right? Yes, and then convert that one. So let me step back. So let me the 30, and then, well, let's might as well just check this first. So we got rid of that, and that should be what the table looks like. Let's go ahead and continue running it with coverage, even though I can't do breakpoints with that. Let me collapse that, and that seemed to have passed. All right, so let's just copy that again, because I like adding to the tests rather than modifying my previous tests. because they all test something different. So if I were to delete 50 this time, this one should be like this, but technically this one should be 60, right? So if I did 50, 60, 80, oops, 60, 80, yep, that's right. 60, 80, 20, 40, 60, 70, 80, 90, yeah. This one would probably fail because I'm assuming that this is the one where we have to borrow from the right and we haven't implemented that yet. Right. Correct. All right. So how do I debug? Oh, cool. Can I drag that one up? Yeah. That way they're next to each other. All right, so let's go ahead and debug this. That one's a little bit more complicated, so let me delete 60 instead, because this is changing the key twice. So if I do that one might be a little bit easier. So let's pause. Let's do 60. Step forward. It's finding 60. It removes it. Then it steals from the right sibling. Which is going to be here. And we basically just need to rewrite this. And I'm assuming that when we were in that before, we were getting a class cast exception. So we need the left node, which is going to be children get location, node of K, right node, children get location +1. So once we get here, we assume that there is a right child because of the fact that we already did the logic outside. So we can get rid of that. All right. So now we're borrowing from the right. So here we want to do left node add. I mean, yeah, we could do that. But I don't want to do that. Because eventually I need to figure out how to associate values with this stuff, and that's just going to add a whole new level. I don't know if I want to do this within the keys, but if I were to add right node. Oh wait, not add. Keys dot add right node dot remove location. No, first 0. Not key. Can I get that as 0? Oh, keys dot remove. So we remove it from the right keys and we add it to the end of the left node. And keys.set location is going to be the right node get first leaf key. Yeah, it doesn't matter which direction I did that in. That's fine. That's weird to have done it that way. I don't think that ever worked. Yeah, that wouldn't have ever worked. I don't know what I was thinking. All right, so we moved the key. So now we need to deal with children. So if left node instance of internal node. Left node, children, add, right node, children, remove 0. I guess in that particular case, I don't think we need to worry about it being a leaf node, except for the other remove. So if I did if right node get children isn't empty, then I can just move the children to the left node last child. Is that it? You think that'll work? That seemed to have worked. And I can come over here, paste what the last one was, and it's this one. Assuming the remove was called last, and it looks like it. I mean, we're not done here, so let's just hit play. So, we need to update that node. Oh wait, we did, what did we do? Oh, we're still removing 50. We need to remove 60. 50. Or no. Oh, I got lost. All right, so we're not deleting 50 anymore. So let me rerun that. Should be 1030. Nope, that is not right either. 1030, 60. Yeah, that's the ones that we remove. So it's 2040, 5070, 8090, and the top two keys are 5080. Yeah, that's correct. Okay. I just forgot that I changed the example halfway through. Okay, there we go. So 5080, 2040, 5070, 8090. So now we have to try the same sort of thing with the removing of the 50. So let's skip back. And instead of removing the 60 this time, we're going to remove the 50. So that's what it should look like in the end. So 60, 80, 20, 40, 60, 70, and then 80, 90 at the end. This one should fail because I don't think I'm updating the, or wait, that needs to be 60. Yeah, 60, 80. This one should fail because I'm not updating the key at that position. Right? Or am I? Oh, I am. When did I do that? Oh, okay. Apparently I got that working too. Okay. Let's go ahead and run this with coverage. I should have taken some Tylenol. All right. Let's take a look at this. I haven't checked to see if nothing was removed yet. That one will be easy. I can just do that one at the very top. So if we for 132, 132, let's try to delete 4. We're going to end up with 123 at the end. So that one should make that one green because nothing was removed since that one was not found. That one should. Oh. No, nothing removed. That shouldn't have removed anything. And it didn't. Did that return true? I mean, we got here. Return false. Why is that? Let me delete that coverage metrics and rerun it and see. No, that's still. What? All right, so this is not the first one. So the first time that we run this, we're going to be returning or removing a 2. Yeah. And let's go to the next one. Here we are removing a 6. Where are we? Degrees 5. I guess that's one bad thing about using parameterized tests. I mean, it doesn't launch you back up to where you're creating the test data. Oh, this is, yeah, this is correct. So weird there. Is it executing in the wrong order? I guess I can look at the console. Oh. Oh, that's right. Ha ha ha. That makes sense. Because we're not testing it, I need more nodes than this to test what I was wanting to test. Because the root node is a leaf node, so it's not calling the remove on an internal node. So I need to do probably this one right here. Let's replace this. This is going to be 1, 2, 3, and 4. And we're going to remove 5, which doesn't exist. Now run that with coverage. There we go. That time it worked. Ooh, gotta get 100% coverage somehow. All right, so now we have to look at merge location -1. So that was location 0, the last one that we did. And technically we're only merging leaf nodes. So that might be an issue, I don't know. All right, so how would I do that? So if the location is 0, it merge. This is if we've already exhausted that the left one is not greater than half and the right one's not greater than half, and we know that the current one's less than half, we're wanting to merge. All right, So in that particular case, I think it would be like if we deleted 70 here, it's going to merge with the right side. Nope, it merged with the left. So if the location is 0, it calls merge on the location. And merge, we already declared that this is always merging with the right. So if the location is 1, it's going to do location 0 and merging with 1, right? Correct, I mean. So that makes sense. So we merge to the left. All right. So in that particular case, we're wanting to delete 70 now. And this will be 80. Oops. 80. 20, 40, 60. 20, 40, 60. Get rid of that. And 80, 90. Yep. And let's see if that one passes the test. Crossing fingers. That seemed to have passed the test. 80, 20, 40, 60, 80, 90. Yeah. So it was able to borrow from the right. I would like to do the same thing, but I would like to, instead of deleting 70, let's get back. I want to delete 60, which should modify that, right? Yeah, it's basically going to do the same thing. It doesn't change anything. So if I come in here and delete 60 instead of 70, this one it'll just be 70 that time. So that test didn't really do anything. I will have to make sure that some of my removals and stuff will be of the appropriate order. But I'm gonna have to figure that one out later. Okay, so I think adding and removing works now. Just double check with the other coverage that we covered everything that we needed to. You know, don't worry about the other searches. We're only caring about the adding and removing. We didn't do anything with this. Location, if the comparator is not null. Oh, it's because the comparator is always not null. So that's actually dead code. Because that was something that I had tried before. So borrow from the left. So we haven't had enough levels to do any kind of borrowing with internal nodes. And we don't care about that one, do we? All right. Yeah, all of the merge is correct. I can probably just go ahead and remove all of this commented out code. It makes me feel good. This will always be null, or non-null. so I don't need that. Okay. So yeah, I guess we only need to test borrowing on multiple levels. That one's going to be difficult. Wish I could automate this. Yeah, that would have been handy. Didn't know I could do that. How can I do that? How can I do that? Let me just set the degree as 3, and let's just start adding some. So if we were to, yeah, we can't borrow from any of these. Not easily, at least. We're gonna have to add a lot of numbers to get to that point. So if we were to delete like 40. Yeah, it's because I'm doing a maximum degree of 3, so all of these can have single nodes, so there's no way I can borrow. So that was kind of pointless. Oh well. Let's just do something weird, shall we? All right, so we're gonna do a 5th degree. But what we're gonna do is 4 and I equals 0. Let's start with 10. I is less than or equal to 200 for now. I plus equals 10. And then I guess in this particular case, it doesn't need to be a list, but that's how I have it. All right, so big keys. Obviously, this is going to fail at first because I don't know what this is supposed to look like without doing some junk in it. And we need to make sure that we have all of the other parameters in here. All right, so that's all the other parameters. I'm gonna get off of coverage, kill that, go to debug. I'm not sure what this is gonna look like, but as soon as it generates the GraphViz stuff, I should be able to at least see what it would look like here. Yeah, it's still not enough nodes to I know this is a weird direction. I didn't spend a lot of time writing this to get all of these on the same rank. You just have to turn your head sideways a little bit. And it's basically organized correctly. So 200, let's try 2000. See what that looks like. Oop, probably shouldn't go to 2000. Looks interesting, huh? It looks very interesting. Can't resize this, unfortunately. So that's the root node. Yeah, node 0 is the other root node. I mean, you can see that even with how many nodes are here? So 2000, like 200 nodes here. Because of the fact that we have 5 degrees, meaning that we can have up to 5 keys in a single node, it distributes them pretty well, and it's able to maintain the graph appropriately. Instead of that, let's do 500. Oops, I don't know why I refreshed. It's not linked to this. So this is with 500 nodes. Or not 500 nodes, sorry. It's going by tens. 10 to 500. Just trying to think of how I can do this to borrow from basically doing merges and stuff on one of these. I mean, we don't have to go up to that degree, so let's do tens to 200. I just want to make sure that there's enough nodes where it has at least like 3 levels. Because I want to be able to borrow or merge the internal nodes to do the other test. And it's not going to be easy. What if I went to 170? I guess I need to do 180 to split that one off. Nope. One more would break these up, and then it will pull one up here, which would require this one to break off, and then it would go one more level. So let me do that one. That one should split that one and split that one. Yeah. Okay. So one. I don't want to do this. This is a degree of 5, right? Yeah. All right. Well, let's do all these manually. Again, I kind of wish that it refocused on that field so that I don't have to constantly click. 90, 100, 110, 120, 130, 140, 150, 160, 170, 180. All right, so the next one should split this one and pull up to merge, and then this one overflows and it would have to pull up again. So 190. There we go. So is that actually what I have? 70, 130, yeah. 30, 50, 90, 110, 50, 170, 10, 20, 30, 40, 50, 60, 70, 80, 90, yeah. And then the last one has the 3. Okay, cool. So that is actually correct. So what I'm going to do is drag that off the screen so I can see it while I create the expected result data for it. So it's this one right here. The keys is going to be 70 and 130. And that's going to have 3 children. Child C. Three children. The first child is going to have the keys 30 and 50, and that's going to have 3 leaf nodes. Heard that. Going to have 10, 20, 30, 40, 50, 60. And this one's going to have the keys 90 and 110 with the leaf nodes 70, 80, 90, 100, 110, 120. And this one is going to have the keys 150, 170 with the 3 leaves of 30, 140, 150, 160, 170, 180. Okay, and I do not want to delete that one. I just want to delete something that doesn't exist so that it still comes up with the correct graph for that. I just want to make sure that it's getting to the deletion part and it's like, hey, I can't do this. Does that look correct? Yeah, that looks correct. No, that is not correct. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 20, 30, 40, 50, 60, 70, 80, and 90. Yeah, this is where it should have, I should have somebody outside my house. Better assertion logging. 70, 180, 190. Yeah, I'm going to be switching back and forth. So sorry about that. 150, 160. Yeah, right? 30, 50, 90, 110, 150, 170. 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160. My head's in the way. 170, 180, and 190. Yeah. How is that not equal? Because it's failing here, which is after I did the initial adding of the other keys. I haven't even removed the keys yet. I mean, technically, I can, if I were to take this structure, paste it here, that should be correct. Because the tree should be left unchanged if I try to remove something that isn't in the tree to begin with. So this one should be successful, but I'm not entirely sure why it's not. Yeah, I have no idea why it's not correct. I mean, this is printing based upon the B tree information, and I'm building the structure the same way for my test nodes. 70, 130. Those are the keys of that top level node. It has 3 children. First child has the keys 30, 50. And it has 3 children, which are leaf nodes. Okay, so let me... Oh, I'm gonna have to bring this over here and take a look at my logging here for my comparison. I should probably maintain a path. Or I can just do this. Let's just throw a, yeah, that should work. Some breakpoints in there. All right, so this is the correct one. All right, so we're looking at this keys is 170 and 180. Yep. And the root keys is 170, 180, 190. Oh. What's that? Nobody in chat saw that? I forgot to add the 190. Man, all that. It was just because I was iterating to 190 and I forgot to actually add 190 to the collection. All right, so now this one should be successful. Crossing fingers. Get rid of that one now. Yeah, okay. All right, so now let's go back to this visualization and let's see what we can do with this. If we were to delete 160, that does borrow, but it doesn't borrow from that. Let's get back. So what I want to do is probably delete this node. So if I delete 190, 180, that's enough to borrow. All right, cool. So 190, then 180. So if things worked out correctly, the root should be 70. 30, 50, like nothing over here changed. Right? Correct. So then we only have 2 children, not the 3. And we deleted 180 and 190, but we're left with 150, 60, and 170 as a child. 130, 140. And those are basically merged over here. Let's get rid of this altogether. So here we have 90, 110, 130, 150. 90, 110, 130, and 150. We have 70, 80, 90, 100, 110, 120, 130, 140, and then the final 3. So this, hopefully that's correct. And that did not work. So what was I left with? Ooh. You can't see that, but that looks weird. That is not correct. That did not remove the right child. That should have gone up there. So there's some logic that's incorrect on the looks like the leaf is okay. Yeah, looks like the leaf nodes are right because we have 10, 20, 30, 40, 50, 60, 70, and so on. Oh, you can't see that. But over here, we have 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, and then the final 3. That's correct. So it's just the issues with merging internal nodes. And this is merging, right? I'm gonna have to figure out how to put a breakpoint for this. Here's one way. let's go back to the remove method of the internal node. So what I want to do is skip back. Let's just make sure that this looks correct, shall we? So I'm going to copy that, paste it up there. Oh. So here we're just removing 190, no longer removing 180. So this one should be correct. Let's just make sure that it's only failing on the last data bits. No, it's failing on that one too. What is this one looking like? So let's copy that one. Good thing I added that debug. If I'm just deleting 180, or 190, I mean. Again, that looks correct. 150, 160, 170, 180. Oh, I don't know. I mean, that looks correct, right? Why is that having a problem now? We comment out this one. I don't know why that's failing. Those basically look the same. I must be missing something. I mean, got streamer blindness right now. 70, 130, 30, 50, 90, 110, 150, 170. And all of those are 10, 20, 30, 40, 50, 60, 70, 80, 90. Yeah, those are all grouped. Yeah, that's correct. Did I just do the wrong numbers here? $170, 110, 30, 50. Yeah, I don't know what's our problem here. Probably need to do that split thing again. Oops. Put some breakpoints on the compare for the false. I should probably just leave those breakpoints. So I'll probably want to see those anytime that there's a failure. All right. So this dot keys is 70. And 130. Oh, man. Blindness. Jeez. Yeah, I need to leave those breakpoints. Okay, so that one should succeed now. I'm just getting tired. I've been streaming for almost 4 hours now. Okay, that one's successful. Ugh, good. All right, back to this one. This monstrosity. So this time, I'm deleting the keys 190 and 180. So if you delete 180, it's going to drop below half here. It needs to borrow. And then it removes the key here, which drops below half, which then needs to not borrow, but merge. This just needs to merge. Let's get back, pause. We do 180, delete. So we go through here, we delete the 180, we're merging the node. And then we're merging this node. And that's it. Okay. Let's see if we can figure that one out. Oh, not in the test. I can, it's all in the internal node. So I need to figure out if this is, it's probably this one. So merging at the location and the one to the right of it. So we're actually taking the ones from the right and moving it to the left. Saying that should have removed the children. Do I have the updated graph? No. I guess I didn't run that. Guess I haven't printed it yet. How is that happening? See, I'm not sure the order of these. I don't know how that's working. This is node 9. So let's take a look at which ones have access to node 9. So this is, oh, that's going directly to node 9. What? Node 10? Do we have a node 10? Hello? Why is my tooltips not working? Yes, G, thank you. That doesn't help. Okay, there we go. Node 10. So node 0 goes to node 10, is that right? Node 0, F1 goes to node 10, right. In what world? F0, F1, F2, F3. Oh, we don't have an F4. So it's not deleting the children reference. Hmm. All right. Let's get back. Play 180 needs to borrow or merge these two. But then it needs to drop that child. One moment, please. I need to figure out, is somebody mowing the lawn? Looks like my neighbor's reseeding their lawn. Lucky me. All right, so merging. This is where I'm having the issue. I thought it was this. Can I put a conditional breakpoint here? Condition. No. Let's come up a level. Let's put a conditional here. The only time we're deleting integer value of 180. Is that the one that we're deleting? Yeah. Equals key. Done. There we go. So here we're deleting 180. So if I were to take I'm curious, can I do this? New graph viz outputter. This to string. Can I do that? Copy value. Ha, that works. All right, so I'm able to basically get what the tree looks like prior to that removal. All right, so here you want to remove 180 and this is an internal node with two children, 70 and 130. 70 and 130. Yeah. Step over that. The location is 2. So 0, 1, 2. So then it grabs the child at 2, which the children at 2 is going to be another internal node. So if I push play, it'll hit this breakpoint again because then we're going to go down a level. There we go. So now we should be in this node right here. So if I take a look at the keys here, it's 150, 170. Correct. So then I step over that. It should return 2 for the location. So this is where it gets interesting. Because here, whenever we remove it, it actually removes it and we come down here. And leaf node remove. Basically, all that does is remove the key. So if we take a look at the children at 2 keys, We only have 170 left. So now location, that's true, and not equal. Is it? No, it's not equal. So the location minus 1, which would be 170. Oh, it is. Right? No. Yeah, I'll just do this. Okay, it's not. All right, so then we come down here. Children at the location. The location is still 2. So if I take a look at children location 2, and I get the key count, it's going to be 1. That is less than half, because we have max keys, which is 4 divided by 2. So 1 is less than 2. So then we come in here. We're first checking to see if we can borrow from the left, which we can, right? No, we're not going to borrow. We're going to be merging. It's actually going to be that one. So if I put breakpoints in all 4 of these, should be the last one. Yeah. So then we merge. So then the merge, it's basically going to be merging play location 1 0. Yeah. So we're at this node. I have to remember that. So we're at this node right here, and we're wanting to merge in the child at index 1 with the child at index 2. So we have left node and the right node. We're wanting to take all of its keys, which we already removed the other 170. So if we come back up here and we evaluate the expression of new GraphViz, outputter tree, or this to string, we copy that value. So this should have removed 180 from that node, right? Nope, can't see that. But I removed the 180 from that node. So now we're wanting to move, basically merge these two. So to merge, we take all of the keys in the right, move it to the left. Well, this doesn't move, it just copies the keys from the right node to the left. And then we add all of the children from the right to the left node. This doesn't have any children, so don't need to worry about that. So if we do that, hit play, pop up a couple of levels, new GraphViz outputter, this to string. So now that should make the 170 go up in here, and this is going to be just a dangling node. Didn't delete it, it just copied the other key from here to here. All right. So now we're wanting to remove the keys at location 1. Right, so that's going to remove that key. And we're going to remove the children at location +1. And location is 1, so 0, 1, 2. So it's going to remove that child link. So it's going to remove that key and that child link. So first I'm going to step over that, come back up here, evaluate that expression, copy that value, paste it back over here and see if it actually removed that key. It did. And now we want to remove that child. So we can step over that one. So now this children 150, 160 should have 3 keys, 150, 160, 170. Yeah. So that removes that child. So if I come back up here, evaluate that expression again, copy that value, paste it. Does that get rid of that node? Well, not yet, because we haven't updated the double link list. Which this one should be correct. So let me hop out of here. And let's just go over these and step out. Okay. So now if we go down here, evaluate that expression, this one should at least get rid of that one node. So that one should be gone now. Yep. All right. So now, because we're still here, that's going to return to its parent, which is going to result here. So now we're in this guy. So 70, 30. So if I take a look at this keys, 70 and 130. Yeah, so we're in this node now. So now we're checking to see if the location is not 0. That's correct. And the child of that location, which is location 2, 0, 1, 2, this child, is that first leaf the same as this? So 130 versus 150, it's not. So that one's not going to be evaluated. And then it's going to say, hey, this child at this location key count is less than half. So that is correct. And then we're going to have to do one of these. And it wants us to merge with the left. Right? Does that seem right to you? So pause. 180. Step forward, step forward, step forward. Delete that. Merging node. Yeah, then this has to merge, which will bring 150 into this guy. Right? Yeah, step back. But it also brings up 130? What? Oh, that makes sense. Ooh, that one's a little bit more complicated. Yeah, because that key needs to, so I basically need to, so if I'm here and I'm merging, I need to grab the first key in all of the children and throw it into this one. Into the left. That's complicated. All right, so let's go into this merge. So that's where we were probably having the issue. How are we gonna do that? I don't know. Oh, apparently I never started captions back up, so sorry about that. I think it was whenever I took a phone call earlier or something. All right, how am I gonna do this? I mean, it makes sense for the these guys, but I don't think this makes sense for the internal nodes. So that's correct. This one is not. So we grab the left node. So we're here. So this is this. So left node is a location. Right node is a location +1. And we're wanting to add all of the keys from the right one to the left one. And we can't do that one yet because the right one has children. So before we can do that, how do we do that? Right node. First leaf key. So yeah, let's evaluate that. So right node. What? Oh, we haven't gone into it yet. Step into. There we go. And play up to that. Evaluate expression. Right node. Oh crap! It's because I changed the code, so my breakpoint ended up getting disconnected. All right, so I need to go through that again. Unfortunately, need to not change code while I'm debugging because it changes the breakpoint locations. Goody. Yep. That's the child. I come out. And this should be the 131. Yep. Then we come in here. Step into that. Step down to here. There we go. So let's evaluate. Right node has 150 in it. Yep. It's 130. Trying to think of how that can work, because if it had more than one in here, if it had like two or three and it's still doing the other merge, I basically have to get this number. And that's the issue here. Just need to figure out how to do this in a way that doesn't break it for leaf nodes. So I guess that's the only time. So if right node get first leaf key is not equal to right node get keys at 1, or the first index. So if it's not the same, it means that there's a child, and we need to add that. So then the left node keys, I guess I can just use filled access, add right node get first leaf key. If it was equal, because I think in the leaf node get first, yeah, it just grabs the first key, which won't be the same for the internal nodes. All right, so then, so if I did this on the internal node, come on, internal node, it grabs the first leaf key of the first child. So it'll just go down the other chain recursively. So we add that key first. Then we add the rest of the keys. We add all of the children. Okay, so the rest of this might actually be correct. So let's remove our breakpoints, pause our breakpoints. Yeah, thought so. So then paste that, and my links should be correct now. Nice. Look at that. Look at that. Look at that. So that did merge. Okay. Because it's always merging with the other right. So that will work for me. So the problem that we had before is that it had too many children attached, but not enough keys, because we forgot to move the 130, because the 130 represents this guy, 110 represents this guy, 90 that guy. This one is just before 90, so none of these keys are here. Okay. Oh man, that was interesting. So that one deals with merges. Glad we tested that, because we wouldn't have known that until trying to add a bunch of data, and we're like, hey, why is our data integrity wrong? So that one solves that issue. One issue that we do have that we're going to have to address is duplicate keys. So right now, I don't think we're doing anything in regards to duplicates. Probably throw an exception if there's a duplicate key found. Maybe. But maybe that's something that we can worry about later. Oh boy. So yeah, that should be correct for all of that. Probably just remove all of those breakpoints and we should be good to go. So let's go ahead and run the coverage test here. Ignore that. Merge. Borrow from right. Yeah, we're still not borrowing if it's an internal node. How do we do that again? So I guess in this particular case, if we remove 50, we would have to borrow from the right. So let me hit play. And if we remove 50, that would have to borrow from the right. Ugh, all right. It'll all be worth it, probably. In the end. All right, so let's just copy that, because that was a different test case. So here we're going to remove in the same order, but this time we're going to remove 50. And let's just repeat this view. That's going to be 90, 30, 70, 110, 130, 150. Yep. 10, 20. 30, 40, 60. And this child gets moved over here. 90, 110, or 100, 110, 120, 130, 140, and 50, 60, 70. Okay. So is that still accurate? It is not. Unless I type something wrong, which is very likely. This guy right here is supposed to be 90. Yeah, 90, 30, 70. So why is that not... or wait, that shouldn't be 90. Yeah, it should be 90. What in the world did I do here? That is totally wrong. I think it's because it didn't borrow correctly. Are the leaf nodes correct though? 10, 20. I know that you can't see all of this. Let me try to do this in a way. Yeah, because my face is blocking. Turn it to the left. Yeah, let's just turn off my cam. There we go. So 10, 20, then group of 3. So these are all in order. 10, 20, 30, 40, 50, or 60, 70, 80, and so on, all the way up to 170. 10, 20, 30, 40, 60, 70, 80, 90, 100, 110, 120, 130, 140. It looks like those were done correctly. It was just the borrowing from the right. All right, so let's debug that one. Oh, notice that it has this now, but it didn't do it correctly. What did we not do correctly? If we borrowed from the right, we should have 30, 90, 110, right? 30, no. 30, 70, what? Yeah, that one should be 70. Let's get back. Oh, interesting. Yeah, it shouldn't have crossed the boundaries like that. That's my mistake. You can't do that with internal nodes. You can't cross that line because the children aren't going to be correct. Oh boy. So in that one, whenever we delete, this one is merging with the left, and then this one needs to borrow, but it can't borrow from the right. It needs to, well, it does need to borrow from the right. Sort of. Let's take a look at that step by step. Delete. So here we delete the 50. We merge that node. So I don't know how that happened. Stealing from right sibling. Step back. Merging node. Yeah, it's going to merge. Wait. 50. Step forward. Is that correct? Yeah, that's correct. Because that key is updated to the first child of that one. So that's correct. Maybe we should step through this. Because we're so far levels deep. My brain isn't able to keep track of all this. All right, so here I want to create a breakpoint conditional. This time we're deleting 50. And let's go ahead and remove the test criteria or overlay. Run this, and we should stop at the 50. Oops, nope. Oh, it's because we paused the breakpoints. There we go. All right, so 50. So this is going to be the first one is going to be an internal node with a single key, right? No, we have two keys, 50 and 90. What? Oh, 50 and 70. Why did I read that as 90? I may have to call it for the day because my brain isn't keeping track of this stuff. So 50, 70. Why? 50, 70. Which one has 50, 70 in it? I don't think something was set up correctly here. $90, $180, $190, $180, then 50. So this is where we were with the 190, and then we deleted 180. 180. And that's what we should have been left with. And that was from the previous, but this one right here. So 70, 30, 50, 90, 110, 130, 150. Yeah, that one's correct. And now we want to delete 50. But something's wrong with that. I don't understand how our node here has the keys of 50 and 70. Like, in what universe did that actually happen? We don't have 50 and 70 in the same node anywhere. Okay, so instead of doing that, let me come up here and let me put the breakpoint here. Ugh, not commit. I don't know why it's doing that. Integer value of 50 equals key. All right, starting that over again. There we go. And before we actually remove it, let's take a look at the GraphViz output. Copy that value. I guess I can get rid of that. Come over here. Let's. Oh wait, what? Did we delete something other than? Oh. I guess I did delete a 50 before. I'm a dummy. Where was I doing deleting of a 50 before? Not there. Not there. Right there. Yep. Or wait, no. Yeah, I was deleting a 50 there and a 50 there. So I've done 50 a couple of times already. Ah, crap. Okay, so there's 3 times that I'm deleting 50. So I need to skip the first 2. 1, 2. All right, so now if I evaluate an expression, new GraphViz outputter, this string. That's much better. Yeah, okay. Yeah, I was looking at like, how are these in the same node? All right, so get rid of that one. All right, so in this particular case, this one, there should be only one key and it's 70. The location is going to be 0. Yep. So then it's going to try to remove from that, which would basically recursively go down into this node, calling remove. So now we're in this node. So our this keys should be 30 and 50. 30 and 50. Yep. So then it has an index of 2, 0, 1, 2. So the location is 2. That's correct. Then it calls remove. Oh. Oh, it's because it's over there. I shouldn't have hit play. What a pain in the butt. Oh, why did I remove the this guy? One, 2. All right. So then come into here, Go there and there. So now we're here. And we call remove on its child, which will remove the other 50 here. And then it's going to be like, hey, your size is less than half. So it needs to probably merge with the other previous one. So then if I go up a level, so I'm back in the 70 node. If I were to grab the current state of things, I probably need to make this a little bit easier. Tree. So it should have at least merged those two. And it did. So now we need to be able to borrow from the right sibling. So I'm assuming it's going to be that one. I just want to double check. Yeah, borrow from right. See, this is where it's going to get weird. Oops, I forgot to delete 180. Okay, there we go. So now we need to delete 50, but I'm going to pause it and delete, step forward, get to the other point of where we're at. So I did that merge. So now it's having to borrow. How is it doing the borrow? Because it's like shifting all the way up. See, this is not just borrowing, this is stealing. Because we will not have access to that up here. Yeah, this is going to be a little bit more difficult. Right. So this isn't borrowing the 90. This is borrowing the first child. So the this stuff will only work on leaf nodes. And this won't work on leaf nodes at all. This will only work on internals. All right, so then the internal, we just need to steal the children. So that's correct. We grab the first child of the right node and append it to here. But then we need to do left node keys, add right node. Probably need to do that first. Right node, first leaf key. And this would add the other 70 as a key to here. I guess that's essentially what this is doing too. Probably gonna have to go back in local history to see how bad I messed this up from my original idea. Probably shouldn't be messing with this. I don't want to break a bunch of unit tests that I've already gone through. So internal node. If the right node has children, means that we're an internal node anyway, so I already know that it's an internal node. Because every internal node will have children. Otherwise, it's a leaf node. Left node keys, add the first key, first leaf key. Okay, that'll do that. And then we remove first child and add it to the children here. So we basically sever this tie and move it to here. And we need to delete that key. I know that I have some repeated stuff in here. So yeah, I think I just need to see what this looks like. If we even get to that point. 1, 2, this is the third one. Or wait, no. Because we have all these extra breakpoints. Let's just play it. Yeah, still not doing it. Was able to move that child to that side though. And it has the correct key. 30, 40, 60, 70, 80. So that's wrong now. No, that's correct. And then this one will need to get updated to the first leaf of the right side. Shouldn't that have done it? That should have done it. All right. It is going 4 hours and 20 minutes. I think I need to call it quits. Yeah, it is already 2:40 my time. So I think what I'm going to do, I don't think this is going to be too difficult. Basically, it's nearly correct, right? The only difference is the 90 there. 30, 70, 110, 130, 150. Oh, I should probably press play. And then 1020, 30, 40, 60, 70, 80. And then the first child here is 90. So yeah, it's basically just lacking resetting that guy. I'm almost wondering. So after all of that, nope. Nope, that is not correct. Oh, index out of bounds. Yeah, it's not going to be that easy. Yeah, so I'm going to do this offline, finish this up, see if I can add any other tests, but we're so close. And then whenever we stream again, we're going to start looking at traversals. I mean, that's what we wanted this for, right? Being able to traverse this. So here's some unit tests that I can do on that, such as returning a range, basically being able to do node ranges between certain values. That might be nice, making sure that we can traverse forwards and backwards across this double link list. And that'll allow us to do all of the cool indexing searches. So yeah, I'm going to call it. So hope you enjoyed this extra long stream. I don't know when I'm going to be back. Probably not tomorrow, but probably for sure next week, Monday or Tuesday, because I got some free time. So I'll see you then. Take it easy.